So now before we continue on to this example, first let's point out a few of the values that we will be working with. And the first thing about each of the examples that you will see throughout this course is that they're going to be much, much smaller than a real system. So a real system and a real cellular are going to have many, many, many more devices than you're going to see them we're going to be working with here. But we're constrained by what we can write on a single piece of paper, and additionally, it will illustrate the main ideas just by considering a smaller example. So now, in this table over here, we're showing each of the three transmitters on this side, A, B, and C, and then the receivers as well. And each of these values is what we call a gain. And the direct gains are for instance, from A to A, from B to B, and from C to C. Those are the direct channel gains. So we can write that here. Direct, this is direct, and this is direct. And what this is really saying from A to A, being 0.9, is that whatever transmit power we start with over here gets multiplied by 0.9, and that is what it gets received at over here. And we look at these as gain values, but since they're less than 1, we know that it's going to be less than what we transmitted at by the time we get to the receiver, because we're multiplying. So it's really an attenuation, but we look at them as gain, just strictly speaking, in mathematical terms. So then from B to B, it's 0.8. So B has not as good of a direct channel gain as A, because you want the direct channel gain to be as high as possible, and C has 0.9 just like A does. Now we look at the interfering gains. For instance, we can say from A, starting at A to B, from A to B is 0.1. So this value over here would be 0.1. From A to C, we have 0.2. So this couples down here 0.2 of that. So whatever transmit power we're at, we multiply it by 0.2, and we get how much power is going to come into the receiver as a result of A. And so we want the indirect channel gains. So each of these dotted lines are indirect. And I'm not going to write all of the indirect. I'm not going to write indirect 6 times. And I don't need to write indirect 6 times. You get the idea. So we want the indirect gains to be as small as possible, whereas we want the direct gains to be as high as possible. We can't always get what we want. And then from B, we know B couples into A as 0.1, and B couples into C as 0.2. C couples to A as 0.2, and C couples to B as 0.1. One thing to notice is that this table is not symmetric. And symmetric would mean that going from B to A is the same thing as going from A to B. So for many of the values here, it actually is symmetric. But for instance, if we look at from C to B and from B to C, they're not the same because we have 0.1 and 0.2. And the reason they're not the same is that different transmitters are going to have different effects on different receivers. Now, the next set of values that we need are based upon the links themselves. So link A, link B, and link C have different parameters. First is the target SIR at the receiver, the target signal to interference ratio. So A wants to get to 1.8. B wants to get to 2.0, and C wants to get to 2.2. And now in terms of noise, as we said, each noise is going to have a certain amount of power. We're in a fraction of a milliwatt here. A has 0.1 milliwatts noise. B has 0.2 milliwatts noise. And C has 0.3 milliwatts noise. So you can see that they have different necessities for differing signal qualities, which will depend upon the specific phone and things along those lines. But additionally, the receivers themselves are going to have different noises too. And C is the worst in terms of noise, whereas A is the best. So in the next segment, we'll walk through the computations of a few iterations of distributed power control, which is the famous solution to the near-far problem.